All right, that's roughly where we were. So last time we started talking about SCET, we said it's going to be a theory that can describe energetic hadrons and energetic jets. Our first example was discussing about a process with an energetic hadron, which is this pink pion. So the pion has a large momentum, large energy. It's much bigger than lambda QCD, it's much bigger than m pi, and it moves basically along a light cone direction. So that was a motivation for us to use light cone coordinates, so we introduce an n and an n bar. And with that n and n bar, which satisfy n squared 0, n bar squared 0, and n dot n bar equals 2, as a normalization convention, we can decompose any momentum, p mu, in terms of components along n bar, and then the remaining two components, which we call the perpendicular components. So we can also write the metric out in these coordinates. And this kind of makes explicit that you have this off-diagonal nature to the basis, that you have n mu with n bar mu. So unlike Cartesian coordinates, where the component along a direction is just given by dotting that vector into the vector you start with, here the component along n is given by dotting n bar into the vector. Okay, and that's reflected in the metric here in the sense that you have these terms n with n bar. So you can do this with any tensor. If you have an epsilon, you can define an epsilon perp tensor, for example, by taking epsilon and putting in an n bar, and then this would be a two-component tensor that behaves in the perpendicular directions as an antisymmetric tensor. And this g perp mu would be effectively living in the little subspace of the perp coordinates. And again, it's a metric tensor there, and this would be the antisymmetric tensor there. Okay. So these are the coordinates we're going to use. So n here had a physical motivation, as you saw from my picture. The pion was moving in the n direction. N bar was just a vector that we decided that we needed in order to define things. So if you have some vector where n squared is 0 and you want to make a decomposition of coordinates, then you're required to introduce a complementary vector, which is this n bar, to make the decomposition for the reasons I said. The simplest choice that you could make if you made this choice for n, so if we choose n to be 1, 0, 0, minus 1, as I did, then the simplest thing you could do for m bar is to pick m bar to be 1, 0, 0, plus 1. So then that would be a light-like vector. It would dot it. When you dot it into this vector, you get 2. And it satisfies all the criteria that we would need. If I choose these two vectors, then I've defined what perp is, because perp is the space that's orthogonal to these vectors. So that's these two coordinates. Okay. So perp in general is defined such that n dot p perp is 0 and n bar dot p perp is 0. That's what it's the orthogonal two directions to the ones that are picked out by n and n bar. So you need to know what n and n bar are in order to define what perp is. So this is one choice. You could make other choices. And we'll come back to this later on. So just by way of example, if I have the same choice for n, but I choose n bar to be 3, 2, 2, 1, that would also be a choice that's equally good. Maybe this to be minus 1. this. Make my choice work. I can switch, well, OK. If we want the same sign, I have to do this. OK, so 9 minus 8, this thing still squares to 0. Dot it, you get 3. Minus 1 is 2. OK, so it still satisfies the criteria that we had here. And it points in some other weird direction. So the point is that this is an auxiliary vector, and there's some freedom in what you pick for it. And once you've picked this, if you picked these two, you would have a different definition of perp. OK, but it's an equally valid possible choice, and we'll actually exploit this freedom later on. But for now, we'll mostly focus on picking the simplest choice. OK, what we're actually interested in describing in these processes is not just the pion, but what goes on inside the pion. What is the quark level process? So we're interested in the constituents. That's where the dynamics are. Is there any questions before I keep going? No. So in this process, b to d pi, if you think about it in the rest frame of the B meson, which is the most natural frame, then the B meson, we've already learned how to describe that. We can describe that with HQET. Same with the D meson. And we know that the things that are inside the B and the D meson are one heavy quark and then a bunch of soft stuff. So I'll call these guys soft because the dynamical part is soft. And so we can use HQET for them. As we did before. And that means we're describing gluons and quarks that are inside these hadrons, where the form momentum are of order lambda QCD. The pion, on the other hand, is what we would call collinear. So as I already described, the pion's energy is much greater than its mass. It's highly boosted. If you were to talk about it in the rest frame, then like the B and the D meson, then the constituents of the pion would have momentum of order lambda QCD. But if you were to talk about the pion in the rest frame, you'd have to talk about the B and the D in a boosted frame. So let's stick with describing the B and the D in the rest frame, or close to the rest frame. The B meson is in its rest frame, and the D meson is slow. And in that case, we're stuck with the pion being energetic. So in rest frame, our pion would be would also have quarks and gluons, where p mu is of order lambda QCD. And we can actually just take that result once we know that and boost it to another frame. So let's just boost along z hat by some kappa that's much greater than 1 as the boost. And the way that light cone coordinates boost is very simple. If you're along the axis of the light cone coordinates, it's multiplicative. So p minus gets enhanced by some amount, p plus gets suppressed by the same amount. That's one nice thing about these coordinates. And of course, p perp doesn't change because it's perpendicular to the boost. So now we can get our pion, which is moving, which should be pink. And if we ask about its constituents, we just boost the components of this 4-vector. So we ask about how they scale. And we look at the different components. The plus, min, and perp scale differently now, so we have to break it up by that. And if we boosted by this amount q, or lambda over q, q over lambda, then that's the scaling for this boosted pion. OK, so now it's got a component in the minus direction. N bar dot p is of order q. That's what we saw before when we decomposed the p, that it was basically q times the light-like vector. And then, but if we talk about, that was the pion. Now we're talking about the constituents inside the pion. Constituents inside the pion fill it out. They fill it out in the perpendicular direction by an amount lambda qcd that's perpendicular to the direction of its motion. And then the plus momentum got correspondingly smaller as the minus momentum got bigger. And so we have that scaling. And so the relative scaling here is what actually defines something being collinear. So the relative scaling of this vector here is that the p minus is much bigger than the p perp, is much bigger than the p plus, and that's what we mean by collinear. It's collimated in some direction, and that direction is the direction of the large momentum. You always have to be careful when you say things like that, because the component along the direction is the opposite light-like vector, but I think you'll always know what I mean. OK, so in the n mu direction, we have a large component p minus, and that defines this thing as collimated in a particular direction. Its perpendicular fluctuations to that direction are small. And so all the degrees of freedom that are in this boosted pion have that type of scaling. So what we're describing, or what we want to describe if we have a field theory for this, is we want to describe, if you like, fluctuations about the pion momentum, which we could just take to be, ignoring the pion mass, we could just take it to be like this. And the fluctuations, the size of the fluctuations we need to treat are things that can fluctuate by amounts of this size. So the field theory is going to have to describe fluctuations about some kind of canonical scaling. And the field theory for this pion is going to have to be describing collinear fluctuations that are of this type. Just like the HQET, right, had to describe soft fluctuations, p mu's of order lambda qcd, ignorant of the heavy quark mass. Here we have to have, it's a little bit more complicated, but that's the kind of thing we want the field theory to do. Any questions about that? So the way that we write this is we say that p plus, p minus, p perp has a particular scaling that we call lambda squared 1 lambda, where lambda is some small parameter and if we have a momentum that scales that way, we call it collinear. So here, so this is generic, any case, with any lambda, and our lambda here was just lambda qcd over q. But if we encountered another physical problem where the lambda was different, we would also call that collinear. All right. So what's a nice way of picturing this, what we're doing here? Because it's a little bit different than you're used to with an effective field theory. Usually with an effective field theory, what you're doing is you're separating modes by their invariant mass. You have things with large invariant mass, small invariant mass. If you think about massive particles, well, that's the invariant mass squared. So if you're separating massive particles from massless particles, or less massive particles, you're really separating things along an invariant mass curve. Just an invariant mass variable is used for the separation. And that doesn't quite suffice here, because as you saw, the pion and the B and the D meson, they both had p squared of order lambda QCD. What separates the pion from the B or the D meson is this more fine structure. So SET is actually an example of an effective field theory that requires at least more than one variable to describe where the degrees of freedom live. So we can draw a picture for what we've been talking about here in two variables. Let's just pick p minus and p plus. And essentially what's going on in this space is you can think that there's degrees of freedom that live in this space at different locations. So out here, if I draw a hyperbola like this, then remember that p squared was p plus times p minus p perp squared, but let's ignore p perp squared for this picture. So if I draw a curve of constant p squared in this plane, then it's a hyperbola. So these are curves of constant p squared. And this one here has p squared of order q squared, which might be mb squared or some hard scale. So any degrees of freedom that live on this curve, or in particular these ones, would be what we would call hard degrees of freedom. And those are something that we want to integrate out of the effective theory. And the other degrees of freedom that we've been talking about have smaller invariant mass. So this hyperbola down here has p squared of order lambda QCD squared. But there's two different degrees of freedom that live on this curve. One of them has a large p minus. That's the collinear one. So it should be pink. And then the soft one lives down there. So p minus here is scaling like, if you like, lambda to the 0. And here, for this soft mode, which also exists in this case, this is actually going to be lambda. So you can contrast that type of picture with a more usual picture, where you would just have one line, and you'd say there's some modes up here and some modes down there, and you'd integrate out these modes, and you keep those modes. This is a little different because you want to integrate out these modes. You want to keep both of those modes, but they live in a little bit of a different place, and that's actually going to be important to formulating the effective theory. So the way that you should think about this is that physically the way you should think about it is that these modes are kind of localized in that region. This is the right physical picture. Which requires another variable besides just invariant mass in order to specify that. All right. The reason we don't have to draw a third direction for p perp is because it was just redundant information. P perp squared is always of order p plus p minus if you're talking about fluctuations that are near the mass shell. For a massless mode, that mass shell is p squared equals 0. And so p perp would just be providing redundant information to our picture, and we just can leave it out. Now, the boundaries of the regions between soft and collinear here seems like an interesting thing to worry about. And that is indeed true. You have to think about how you want to set up this effective theory. And of course, as I have been emphasizing earlier in the course, the easiest way to think about momentum degrees of freedom is with a Wilsonian picture. That makes physically what's going on very clear. So the simplest thing would be to introduce a Wilsonian cutoff. And set this up as a Wilsonian effective field theory. And then we would just take these regions and I would literally carve them out in the way that I drew. I would carve out some cutoff between them, and I would decide who's in the soft region, who's in the collinear region, based on those hard cutoffs. But we don't want to do that, actually, because it would mess up all sorts of symmetries. In particular, it would mess up gauge symmetry, which is an important thing when you're talking about gauge theory. So we're going to use dimensional regularization, as we have for other problems. And that actually will still leave us with this picture, which I drew as a cartoon. It'll still be correct to think about that the modes live in those places in dimensional regularization. What's a little bit harder is how to think about the cutoff, and we'll treat that in some detail later on. So it's still the correct picture. But treating the region overlaps with dimensional regularization is a little more tricky. But at least we can do it in a way that preserves the gauge invariance. Okay, so that's going to be our mode of operation. This theory has a name. It goes by the name SCET2. That's why I called it SCET2. We'll come back in a moment to what SCET1 is. So I could say that the degrees of freedom in this theory, the one that we've been talking about, are some collinear degree of freedom that's associated to some direction, some collinear degrees of freedom, as well as some soft degrees of freedom. And when you have effective theories that are like this one, where the soft and collinear degrees of freedom live on the same mass hyperbola, they're called SCET2 theories. And these are really the kind of theories that you get when you're talking about energetic hadron production. So, any questions so far?